Hi, we are now going to study undecidable languages. So, is there anything that the Turing machine cannot do? Now we are going to give such a language that cannot be recognized. We're going to define the language ATM for accept TM, which is the language of pairs, MW, where M is a TM and M accepts W. We're going to prove that ATM is undesirable. So what does this mean? It means that there is no program that, given a program, given an input, can say if the program accepts the input. Interpretation. Your friend comes to you with a piece of code M and some input W and says M accepts W. And nobody can tell if your friend is right or wrong. But wait a second. Can't you just run M on W? What do you think? No, you can't, because M on W may never halt, but a decider must halt. You want to decide this question, so you cannot just simulate. Your friend is claiming that eventually M accepts W, but you have to decide this in a finite number of steps. Okay, we're going to prove this theorem that ATM is undecidable. And the idea is a proof by contradiction. We are going to assume towards the contradiction that we have a decider D for ATM. Using D, we're going to derive a logical contradiction, something which is impossible. And this means that the assumption 1 has to be false. D cannot exist, and so ATM is undecidable. The key step is how you're going to use D to derive a logical contradiction, and here is where the beauty and the creative step of this proof lies. We're going to construct another decider D prime, and we're going to show an input Y that D prime cannot accept and cannot reject. So D prime cannot be a decider contradiction. Okay, so what is Y? How are you going to do this? Y is D prime itself. We are going to run D prime on its source code. So this looks fancy, but actually it's common experience, right? You can run programs on the source code. I can write today, a program and write on the source code. You have a, C compiler. You can run the C compiler on its source code. So these things are very legit, and we're going to explore them now. And this definitely sounds paradoxical. Indeed, it is closely tied to logical paradoxes. Okay, let's make this more precise. We're going to assume that D decides ATM. And I'm going to construct another decider, D prime, that on input W, on input M is going to run D on M. And if it accepts, it's going to reject. And if it rejects, it's going to accept. So it's going to flip the answer. First question is D prime a decider? I claim it is. I claim D prime is a decider. And that's because, well, look at what I did, right? D is a decider. All I'm doing is running D and complementing the answer. Because D is, and you're just doing simple stuff. However, now the beauty of this logical argument is what follows. What happens if D prime accepts W? Let's think of running D prime on itself. Let's think again of running D prime on itself. Let's say D prime accepts W. What does it mean? If it accepts, it means, how do you accept? Well, you accept if you reject this, right? It means that D on D prime rejects. How was D defined? Well, D was supposed to be a decider for this. So that means that D prime rejects D prime. contradiction. What if D prime rejects D prime? Well, you reject if D accepts MM, right? That means that D accepts D prime, but how was D defined? It was supposed to be a decider for ATM. It means that D prime accepts D prime. Contradiction. This is a contradiction either way. So D cannot exist.